I'm gonna go live now. All right, so okay. So hi everyone, welcome to the CTEQ webinar. My name is Royon. I'm a faculty at Michigan State University working on hadron structure using lattice QCD, and I will be your host today. We also have two speakers on our panelists and Pablo, my co-organizers. Also, we'll be taking questions in the Q&A when we can all rephrase your question later on during the talk process. And we had two back-to-back about half an hour talk on theory and experimental efforts on the Odderons. And so we know everybody is busy. And so we were doing the talk presentation. We will only interrupt speaker if there are conversational important questions that might affect everybody's understanding of the talk. Otherwise, we save most of the question later on. We will have about short 5 minutes question time in between. And if you have questions, you can type in, or you can also raise your hand during the time and we will unmute you so you can ask question on your own. If you do have technical difficulty for different Zoom version, may have issue with a microphone during the webinar setup, and we can read your question for you as well. And after the second talk, we will have a longer Q&A section that we can ask for more complicated and longer answer questions. And so our first speaker is going to be Yuri Kovchegov. He is a faculty at Ohio State University. He's AAAS fellow and APS fellow and have won Soccer Prize. And he's known for his contribution for understanding the structure and dynamics of strong color field in the nucleon and nuclei at a high energy. And today he's going to lead us to the theory effort on the understanding of the Odderon. Yuri?
Okay, thank you very much. Thank you, Royon. Thanks to the organizers for having this nice event. So my goal today is to overview the theoretical background for the Odderon, to give some idea of where we stand as theorists on the issue and why we expect the Odderon to be there. So the outline of my talk is as follows. I'll first give some general arguments why we expect the Odderon to be there and to be non-zero, and start with lowest order perturbative calculations of the Odderon. Then I'll move on to the Odderon problem. The Odderon problem is a problem of sort of determining the high energy asymptotics of the Odderon. And I'll discuss the standard T-channel approach to the Odderon problem. And if time allows, I'll mention a more modern, maybe S-channel solution to the Odderon problem. The result of all those two bullets would be summarized in the fourth bullet, that the Odderon contribution appears to be practically energy independent, with a caveat that, as long as you don't include saturation effects, that is the case. And I'll conclude by outlining a path that people could take to measure the Odderon, and that would connect to the second part of the talk. What is the Odderon and why it's non-zero? So let's start with going back into the 1960s and before. So pre-QCD days, people are looking at various hadronic scattering cross sections. They see that they grow as powers of energy. So like sigma total grows as a power of center of mass energy S, and this power, more modern number for it is about 0.08, so positive power, not terribly large, but positive. And this behavior was described by an exchange of a T-channel exchange of a particle called the Pomeron, named after Isaac Pomeranchuk. He'll be mentioned later in the talk as well. And a Pomeron is an object carrying vacuum quantum numbers like 0 spin, 0 electric charge, 0 flavor, and a C parity of +1. It was sort of called as this hypothetical particle, maybe a composite object as we understand now, made of course of gluons and quarks. So the exchange of this pomeron gave a power of energy growth of the total cross-section. Then, of course, by optical theorem, so if you have a pomeron, say, responsible for elastic scattering between hadrons A and B, then by optical theorem, you can take the forward scattering amplitude, the elastic scattering amplitude, take its imaginary part, and get the total cross-section. So the pomeron is really something that contributes to the total cross-section between two hadrons. So this was all very well, but then people started asking questions. What happens if you scatter matter on an antimatter? If you just scatter like antihadron on another antihadron, this is related to what we just discussed, hadron-hadron scattering just by interchanging initial and final states. But the question, maybe a more subtle question, is what happens if you keep, say, the top hadron the same? So this is some hadron species A, and at the bottom here, we, instead of a hadron species B, we put this antiparticle, antihadron B bar. So now we're scattering matter on antimatter, and the question is, what happens to the cross-section? With the cross-section in high-energy scattering, I forgot to mention, we are interested again, we are interested in a high-energy limit where the energy is large, but T is fixed, so Regge limit. So in the same Regge limit, what happens to scattering of a hadron on antihadron? Well, naively speaking, you say, well, we have the pomeron, right? If the pomeron really is an object that couples to hadrons, why can't it couple to antihadrons? Shouldn't it give the same cross-section in asymptotics? And loosely speaking, this type of philosophy gives you something called Pomeranchuk theorem, which in its more refined form is stated here that the ratio of, say, proton-antiproton scattering cross-section, total scattering cross-section, over the proton-proton scattering cross-section in a limit of energy going to infinity, the ratio is equal to 1. So you look at this relation and you say, oh, okay, that's clear. The two cross-sections are obviously equal. Well, it turns out that it's actually not quite true. The question then, whether the fact that the ratio of two objects in the limit of infinite energy is 1, does it mean that their difference in the same limit of infinite energy is 0? And if you think about it for a little bit, you realize that that's actually the second statement does not follow from the first one. Here is an example, and that's just a hypothetical mathematical example. The statement that the ratio of the two objects in the high energy limit is 1 is really a statement about the leading behavior in that limit, right? So if I take two cross sections, for instance, if the leading at high energy term is log squared of energy, then the requirement that the limit is 1 translates into a requirement that the coefficient here is the same, a log squared, as in both cases. But you may have subleading terms which grow smaller than the leading log squared s. For instance, I put here a log s term. I could also just put a constant here. As long as those terms don't vanish in the s goes to infinity limit, they will give us the difference between the two cross sections, which does not vanish, and in this example even actually diverges when energy goes to infinity. So clearly, the fact that the two cross sections, the ratio of the two cross sections approaches 1, doesn't mean that the cross sections are equal. You may have a non-zero difference between interaction with between proton, say, and antiproton, and proton and proton. There is a variation on Pomeranchuk's theorem called Cornell-Martin theorem, which is the same statement, but for differential cross sections. So for elastic scattering of a hadron on antihadron or hadron on hadron, d sigma dt in pp bar and pp, the ratio is 1. And again, doing the same kind of thinking, we conclude that that doesn't mean that the cross sections are identical really in the high energy limit. So what does it mean? If the cross sections could be different, that means there could be some sort of an interaction, which is not as dominant as the Pomeron, but nonetheless important and non-zero in a high energy limit. And this interaction may generate a non-zero difference, even measurable difference in the two cross sections at high energies. So this is exactly the thinking which led Leszek Lukaszek and Basarab Nicolescu in 1973 to suggest that there may exist an object responsible for such interaction that makes interaction between matter and matter and matter antimatter different, strong interactions. And the object was called the Odderon. So the Odderon is defined as the difference between the elastic scattering amplitude, say, of a hadron on a hadron minus the scattering amplitude of a hadron on anti-hadron, B bar. So Vlodek is saying there is a typo in d sigma total. Yeah, okay, so it's d sigma dt. Very good, thank you. So the difference between the two scattering amplitudes is given by the Odderon. And by definition, you can think of the Odderon as an exchange, as a C-odd T-channel exchange at high energy. So something that couples differently to with different sign to hadrons versus anti-hadrons. Okay. So and this difference, as you saw, need not to be zero in high energy. There's a hand raised, Ivan. What should we do?
All right.
May I suggest that we save it for the 5 minutes after you talk?
Okay. All right. So sorry, moving on. So this is a suggestion that the Odderon should be non-zero. Let's move on and say, well, okay, this is all very good, but now, of course, we know QCD. So what is the Odderon in QCD? What is this interaction that is responsible for the difference between, say, hadron-hadron and hadron-antihadron scattering? And if you start thinking about it, just going from the lowest order in QCD, right? At the very lowest order, if you so instead of hadrons, I'm colliding, I guess, mesons. You can think of them as some quarkonia with quark-antiquark pairs in each. So if you exchange just one gluon, yes, that would give you something C-odd, but it's not color singlet. It cannot contribute to an elastic amplitude. So a single gluon exchange cannot give the Odderon. Two gluon exchange, of course, can be color singlet, but it's not C-odd, it's C-even. And a two gluon exchange does not contribute to the Odderon. It actually contributes to the Pomeron at the lowest order. What about three gluon exchange? Well, that actually works. It can be both color singlet and C-odd, and that's the Odderon at the lowest order. So what one needs is to do to obtain an Odderon contribution, one needs to exchange three gluons. If you look at it more closely, the gluons have to be in a DABC color state, so a completely symmetric color state, which exists only in color groups SU3 and larger, right? If the color group was SU2, there would be no Odderon. But for SU3, we do have an Odderon like this. In my notation, this kind of disconnected gluon means that the gluon can connect either to antiquark or quark, antiquark or quark in this diagram. Okay, you say very well. So we know what the Odderon is, just a three gluon exchange. You go ahead, you calculate, you get the scattering amplitude like this. All these objects here are distances between in transverse plane between quarks and antiquarks in the two quarkonia. Oh, this is a typo. This should be alpha s cubed, of course. I apologize for this. And you have some coefficient which depends on the number of colors and C. Okay, what's notable in this expression, though, is completely independent of energy. So Odderon is a three gluon exchange, which is independent of energy at this order. And the question is it true to higher orders? There are obviously higher order radiative corrections. Would they leave the Odderon energy independent? So that brings us to something called the Odderon problem. So the Odderon problem, to help us understand it better, let's start with actually the Pomeron, the C-even exchange. which at the lowest order can be thought of as a two-gluon exchange, again, taking two quarkonia as an example. So a C-even two-gluon color singlet exchange gives us a Pomeron, the lowest order QCD Pomeron. And then if you're interested in its high energy asymptotics, you have to dress this diagram by higher order radiative corrections. Without going into the details of the calculation, let me just show you the result of this dressing. The result is actually the diagram on the right here. We have the so-called ladder diagram where we take the original two gluons, we dress them, and these T-channel gluons now become so-called regiized gluons. That's why they're shown by somewhat thicker lines. And if need be, I can answer questions on what these are. So those are effective gluon lines which are dressed. And then you build a ladder of S-channel gluons, connecting them. Each globe here is also an effective so-called Lipatov vertex. It's not your regular triple gluon vertex in QCD. These are Lipatov vertices. So out of those effective objects, one builds a ladder. And then these rungs of the ladder, each of them brings in a power of alpha strong. And if you integrate over the phase space of this gluon, you generate a log of energy as well. Oops, sorry. And this way you get the ladder, the BFKL ladder. And to resum it, you write down the BFKL equation, which says that the amplitude, high energy scattering amplitude generated by BFKL ladder in one step of evolution in energy, so you differentiate it with respect to log of energy, is given by an emission of, say, an extra rung of the ladder, which gives us alpha S, some integral kernel times F. So this is the BFKL equation, and its solution gives us the Pomeron behavior. It gives us power of energy behavior of scattering amplitudes. Well, what about the Odderon? Can BFKL equation be scaled up, generalized to describe the Odderon? And the answer is yes. In comes the BKP equation due to this gentleman on the right of the slide, Bartels, Kwisinski, and Przelovich. I apologize, that's the best picture of Michal I could find online. So BKP equation, oops. So again, this is the BFKL equation. It's a ladder made out of two regiized gluons with those effective vertices. BKP generalizes this approach to any number of T-channel gluons. And specifically, since we're interested in the Odderon, I'm drawing on the right-hand side the case of three regiized gluons, which talk to each other by these pairwise interactions. And you can write down an evolution equation. On the left-hand side, we have the BFKL equation. On the right-hand side, we have the evolution equation, which is the BKP equation for the Odderon. And you can see that it's a more complicated equation. It has three different terms because the way you can connect this rung, there are three different ways you can connect those rungs. You can connect lines 1 and 2, lines 1 and 3, and lines 2 and 3. And you get three terms in the kernel. So again, on the left is a Pomeron, on the right is the Odderon. The Odderon problem then is a question of how do we solve the BKP equation for the three regiized gluons in the DABC color state. How do we find the solution that we know is the most general solution of the BKP equation? So let me dwell on it a little bit longer. So we have this complicated equation. We want to solve it. An example is, say, for BFKL, the solution is known because early on, right after BFKL was written, the BFKL authors themselves constructed a full set of eigenfunctions of BFKL kernel. So they exhausted completely the functional space there and obtained the high energy asymptotics resulting on the set of function. For the Odderon equation, for the BKP equation for three regions, the same program is hard to carry out just because it's a harder equation. So there are various solutions, which I'll list in the next slide. But the trick was how to prove that those solutions really are not missing out on some subset of functions which generate maybe an even more dominant high energy asymptotics. But in a nutshell, the Odderon problem is really the problem of determining the high energy asymptotics of the Odderon.
Yuri, just a very quick question. What is Y in this?
Oh, I'm sorry. It was defined somewhere here. Yes. So Y is log of energy, so something like rapidity. And what I had in the previous slide, I had BFKL evolution in energy. It's sort of more compact to write it as an evolution in rapidity, but it's the same thing. It's a log of energy over some transverse momentum scale. What's important is we're just differentiating with respect to log of energy on the left. Does this make sense, Pavel?
Yeah. And F is the forward amplitude?
Yeah, it's, I don't want to go into such details, but you can think of it as a forward amplitude. It's an object you can connect to the two quarkonia, for instance, to obtain the forward amplitude.
Okay, and O is the same for the Odderon.
O in BKP is the same for the Odderon. You define something called the green function, the BFKL green function, or the BKP green function. Essentially, everything. Let me see if I can really quickly annotate. Actually, I can't. All right, maybe that's for the better. So everything, everything between the two quarkonia scattering. So everything in this ladder is F. Everything in this more complicated ladder on the right is O.
Okay, thank you.
Okay. All right, so this is the Odderon problem. What solutions have been constructed over the years? Back in 1998, Yannick and Wozniak constructed a solution, an Odderon solution, with a negative intercept. So when we say the intercept, right. So when we talk about the Odderon amplitude, it scales as S to the power of this power alpha Odderon minus 1, which in the Regge theory jargon is called the intercept. Sometimes alpha Odderon itself is called the intercept, sometimes alpha minus 1. It's a question of convention. But I'll be talking about this power of alpha minus 1, alpha Odderon minus 1. And in the Yannick-Wozniak solution, it's negative. That means the Odderon should fall off with energy. A year or so later, Bartels, Lipatov, and Vaca found the solution, the BLV solution, which actually turned out to be more dominant than Yannick and Wozniak solution. It is a solution which gives alpha minus 1 of exactly 0. And it leaves the Odderon energy independent. Remember, at the 3 gluon exchange level, the Odderon was energy independent. Now we're calculating, or these gentlemen here calculated the infinite power of corrections, radiative corrections to it, and they're still finding energy independence of the solution. A couple of years later, Karchemsky, Kotansky, and Manashov did a very impressive calculation using analogy between this multi-region amplitudes and Heisenberg spin chains, and solving those spin chains with beta ansatz. They reproduced the intercept of Yannick and Wozniak, and then actually found the intercept for 5 gluons, which also is C odd, and conjecture that for any odd number of gluons, then the number of, when this n goes to infinity, the intercept approaches 0 from below, sort of kind of getting closer to the BLV solution. So that is the status of the known Odderon solutions. So let us dwell a little bit more on the BLV solution, but maybe just for a second. Like I said, the BLV solution tells us that the power of energy with which the Odderon grows is 0 at the order of alpha s. Of course, it leaves open the alpha s squared corrections and beyond. So this is kind of an interesting result, that the Odderon seems to be energy independent. But is this the right solution? Maybe there is some other solution out there of the Odderon equation which gives even higher energy asymptotics. And to answer this question, let's tackle this problem in a somewhat different language, namely using the S-channel approach. So shifting gears a little bit, we go back to this 3 gluon exchange diagram, which again gives us some cross-section which is a constant independent of energy. If it's the Odderon exchange should change the sign. if we interchange the quark and anti-quark in our quarkonium. So that's a property on the right-hand side. Now, suppose we want to study the high energy asymptotics, and for that we can use the technology of a small X evolution using the different approach, the S-channel approach, where we say we go to the rest frame of the target. So in these diagrams, the target could be a nucleus, but it could be a proton as well. And what I'm saying on this slide is not specific for the Odderon. Again, originally this is more constructed for the C-even exchange. If we start looking for quantum corrections which contribute to high energy asymptotics, those would be corrections with long-lived S-channel gluons. And each of these corrections, of course, come in with an alpha S power, but also, again, integrating over phase space, it generates power over the log of energy, or equivalently rapidity y. So it seems like to address our lowest order 3 gluon exchange by high order corrections, one needs to emit those long-lived gluons and resum a whole cascade of long-lived gluons. So how is it done? And to do that, one may invoke, for instance, the L-Muller's dipole model, which says that we can take the large NC limit and at large NC, each gluon line can be replaced by a double quark-antiquark line, where quark and antiquark are in a different color because 3 cross 3 bar we know is 1 plus 8, generalizing it for NC cross NC bar, which is 1 plus NC squared minus 1. If NC is very large, we just have NC squared minus 1 dominate. So that means gluon is roughly quark and antiquark in different color representations. So replacing this gluon by a quark and antiquark would change our original dipole, quarkonium dipole, into 2 dipoles, blue anti-blue, red anti-red. And subsequent emissions only generate new dipoles. And at large NC, each dipole scatters and interacts independent of all the other dipoles. So one can introduce a notation for these dipoles. So we have this dashed line, which kind of represents the interaction with the target. And then we have the double line, which represents the gluon emission, which splits the original dipole into a pair of dipoles. And the emission could be in all possible ways, but we kind of abbreviate it with a single disconnected line like this. There are also virtual diagrams. Bottom line is, skipping all the technical details, one can write down this dipole equation for the Odderon amplitude, which turns out to be quite simple. And it turns out to be exactly the same as the equation you write for the BFKL Pomeron in the same dipole approach. And that was this equation was written in this works down here. So we have an equation which we actually know how to solve because it's exactly like BFKL equation. Now, what's the difference in this approach between the Odderon and the Pomeron? Really, if we have the same equation describing the Odderon and Pomeron, the difference has to be somewhere. And the difference is in the initial condition. Remember, the initial condition for the Pomeron is a 2 gluon exchange, which is C even. The initial condition for the Odderon is a 3 gluon exchange, which is C odd. And those different initial conditions project the equation on a different subset of solutions. And this kind of explicitly shows that at least in this dipole world, there is no other solution, that we only have the Odderon. Well, we have BFKL equation for which we know exactly the solution. So, and it could be the BFKL dipole version of BFKL can be solved, and again reproduce the solution by Bartels, Lipatov, and Vaca. I don't have the time to discuss this in any detail. So before I conclude, let me dwell a little bit on what we know about the high energy asymptotics of the Odderon. So as I described above, the BLV solution showed that the power, the intercept of the Odderon, is 0 with the accuracy of alpha squared. People also looked at high order corrections. Cyril Marquette did it, and myself independently at different times. And it turns out that in the NLO, the BFKL, knowing the NLO BFKL solution allows one to understand the intercept of the Odderon. And again, it is 0 with the same accuracy. So that doesn't change. Simon Caron-Hood constructed a very elegant argument which showed that at least at large NC, to any order in the coupling alpha S, this power alpha Odderon -1 is 0. So it should be at most NC suppressed. Further, there are ideas CFT calculations by these gentlemen which showed that at strong coupling, at least in n equals 4 superring Mills theory, the Odderon intercept is also 0 with the accuracy in the expansion in the inverse powers of lambda, which is a 2 coupling constant. So it seems very mysterious. It seems like all the calculations give this 0 power for the Odderon, and one may even wonder whether there is some sort of a symmetry protecting the Odderon, but that's not entirely true. I don't have the time to talk about it, but saturation corrections seem to lead to the Odderon amplitude, which would actually eventually decay with energy. So as long as we are in a linear regime outside the saturation region, then the Odderon intercept, well, the Odderon solution is just a power of energy, but 0 power of energy. Saturation may lead to the Odderon actually decreasing and will lead to the Odderon decreasing with energy. So the protection is only in the linear regime outside the saturation. Okay, in the final 0 minutes I have, let me just say a few words of how to measure the Odderon. So the BLV solution actually contributes to the real part of the elastic forward scattering amplitude as shown by this gentleman 16 plus years ago. So for instance, a scattering amplitude for a dipole for quarkonium can be written as S matrix for quarkonium can be written as 1 minus the real part of the S matrix, which is the imaginary part of the amplitude, plus the Odderon contribution, which would be the real part of the scattering amplitude. But the total cross-section, of course, is given, as we know, by the imaginary part of the forward scattering amplitude. This is the optical theorem. So what can we do, right? It seems like the Odderon doesn't contribute to the total cross-section. Instead, one looks at the elastic, at the differential cross-section, the sigma dt, and which is proportional to the amplitude squared, which has the real part squared plus the imaginary part squared. So the Odderon contributes to the real part of the scattering amplitude. Like I said, the Pomeron is in the imaginary part. So in this model, this is great. Odderon will contribute to the sigma dt. The problem is if you compare PP and PP bar scattering, between them, the Odderon flips sign by definition of the Odderon. But if the Odderon comes in squared, right, the real part of amplitude squared, flipping the sign doesn't change anything. So if this was the entire story, you would not see Odderon in a difference between PP and PP bar collisions. However, we also remember that the Pomeron, say BFKL Pomeron, doesn't only contribute to the imaginary part of the scattering amplitude, it also contributes to the real part of the scattering amplitude. That contribution is alpha S suppressed, but alpha S is not necessarily very small, say in PP collisions, right? So the end result is that the difference of the differential cross-section in PP minus PP bar is proportional to an interference term between the Pomeron and the Odderon. And therefore, if you measure this difference, you do become sensitive to the Odderon scattering amplitude. And you can see papers by these gentlemen down here. So in preparation to Christophe's part of the talk, one introduces a rho parameter, which is the ratio of real to imaginary part of the forward scattering amplitudes. And then using the optical theorem, one can prove the following formula relating this rho parameter to the sigma dt and Christophe and the total cross section, and the sigma dt at t equals 0, the optical point, and Christophe will use this formula more in his talk. Finally, before I conclude, let me just say a few words about searches for Odderon in the electron-proton collisions, as in deep inelastic scattering that was done at Hera. People were looking at pseudoscalar meson production. So in a process where electron emits a virtual photon, which splits into a quark-antiquark pair, which then interacts with a proton, and produces a pseudoscalar meson like pi0 or ATC, my understanding is that there was no definitive evidence for the Odderon, but I refer everyone to the review by Carlo Everts. Finally, I had no time to talk about the Odderon role in spin physics, given the time constraints, but the Odderon does give important contributions to spin physics. The Sievers function at small x, the gluon Sievers function, was shown to be dominated by the so-called spin-dependent Odderon, and therefore scaling as 1 over x at small x, by these gentlemen, Bohr, Echevarria, Mulders, and Zhao in 2015. And my student, Gabriel Santiago, and myself are preparing a paper now generalizing the statement to the quark-Sievers function. And those quantities can be observed at the future electron-ion collider. So that's it. Thank you for your time. Let me just summarize that one can think of the Odderon as a C-odd T-channel exchange. It starts in the perturbative calculations of the 3-gluon exchange level. Its evolution is given by the BKP equation, which allows for this BLV solution, which gives essentially an energy-independent Odderon exchange. In S-channel approach, I showed you that the Odderon obeys the same BFKL equation as the Pomeron, again giving the BLV energy-independent solution. And therefore, it seems like, to the best of our knowledge, the Odderon is energy-independent, at least outside the saturation region in QCD and even in N=4 super Yang-Mills. And the Odderon contributes to the real part of the scattering amplitude. Therefore, it can be seen in the difference of d sigma dt in PP versus PP bar, as Christophe will discuss next. Thank you very much.
Okay. All right, thank you for the very nice summary. We're gonna take a few short questions. Tao?
Yes. Hi, Yuri. Can you hear me?
Yes. Hi, Tao.
Hi. This is Tao from Pittsburgh. I have two simple questions. First one is that what happened to the crossing symmetry between PP and PP bar scattering?
Oh, nothing. The crossing symmetry is there. So of course you can think of it as a crossing symmetry. It's not that, well, the two amplitudes, so PP and PP bar, are related by symmetry, right?
Right.
So you have to extend the first amplitude in you have to swap U and S, right? It's that's your crossing symmetry. And the first amplitude on the left is in a region where S is positive, U is negative. And then in that language, the one on the right would correspond to the U from the left being positive and S negative, right? So there's no statement that they have to be the same, right? So if you take, I don't know, one of those examples, replace S by negative S, which is U, right? So you would certainly, in a leading log, you would affect subleading log, right? So at this order where you have the difference, you will have a difference.
Yeah, this is where I was confused. Looking at these two expressions, they don't seem to satisfy the simple crossing relation.
Yeah, this is just a mathematical example. This is nothing to be. Yes, I could have done better and wrote down something which satisfies crossing. This was just an example to illustrate the mathematical point that if you have a limit of the ratio being 1, it doesn't mean that the limit of the difference is 0. You're right. This is not a very physical example. Yeah.
My second question should be short too. When you try to derive this intercept, this alpha power, does this violate the Froissart bound? The Froissart bound states that the cross-section can grow at most logarithmically, right?
Right. So Froissart bound indeed would be violated if that was the whole story. Thank you for the question. It starts with BFKL Pomeron. Where is it? Yes. Right. So BFKL Pomeron gives us a power of energy growth, and it's been known pretty much ever since it was written down, that would violate unitarity. So that's why our modern understanding is that BFKL equation is not a true high energy asymptotics of QCD. It's an asymptotic regime, but it will get superseded by something called saturation physics. So I had somewhere, I didn't have time to show, I had a few slides on saturation physics, but let me just flash them. I also don't have the time to discuss them now. So really, the evolution equation nowadays one uses is a nonlinear equation, which has a BFKL evolution on the right-hand side as part of it, but it also has a nonlinear term, so that when the amplitude gets large, nonlinear term will become important and will stop this power of energy growth. And this is the phenomenon I was referring to as the saturation phenomenon. So the power of energy for the Pomeron indeed violates unitarity, but it will be, it does get unitarized by the nonlinear evolution. Now for the Odderon, there is no, well, okay, so for the Odderon, there is a similar phenomenon. The power of energy, even the zero power of energy, of course, the zero power of energy doesn't violate anything, right? That's good. That's what we get from the linear evolution. But saturation effects also will come in, and they will come in with a minus sign, and they will not only slow down the growth of the Odderon, there wasn't much growth to start from, they will actually introduce, oops, sorry, what did I click on? They will introduce suppression of the Odderon amplitude. This is what I kind of said very briefly towards the end of my talk, that once we're in a high energy regime where unitarity corrections are important, they will also start suppressing the Odderon, and that adds challenge to the experimental detection of the Odderon at high energies.
Okay, thanks. Thank you.
Sure.
Tim?
A very, very nice talk. I really enjoyed it. I just wanted to mention. I just wanted to mention that I in the past I had collaborated with Chungyi Tan and Rich Brower, and we had actually followed up on that strong coupling model, and showed that there in that strong coupling model there actually is two solutions as well, just like in weak coupling, and one of them is negative, and then one of them is fixed, appears to be fixed to all orders in the coupling, just like the dipole large NC calculation that Simone had done. So there seems to be a lot of agreement there. I just want to point that out.
Right. So sorry, I kind of cherry picked one of those solutions. I'm aware that there is more than one solution. In my defense, I picked the solution which is appears to be more dominant at high energies. Right. The other solution, like you said, had a negative alpha minus one. So my feeling is, okay, I don't remember, I have to look back in the details of ADS calculations, but somehow, well, I would naively guess that the zero intercept solution would dominate, but the puzzle I see here is, why is it zero? It seems to be just a non-perturbative exact statement that the intercept of the Odderon is zero, and I don't understand why, right? When something is zero non-perturbatively, there's usually some reason for it, like a symmetry or something, and I don't know of it. I don't know of such a reason. Please go ahead. Sorry.
Oh, sorry, I had to interrupt now. So we do have another talk, and I understand everybody is very interested in the topic. That's great. But our speaker does have time cut out as well, so we do want to make sure we cover the second talk. Our second talk is going to be covered by Christophe. He is a Foundation Distinguished Professor at the University of Kansas. He has been working on D0 and C experiments for a while, and he especially have won the Humboldt Prize for the small scale structure and high energy interaction on the proton and nuclei. And according to Wikipedia, one of the main reasons that Kansas selected him to join their faculty is to find the Odderon. So this is really exciting news for everyone. Let's hear more from him.
So thank you. Can you hear me?
Yes.
Okay. Okay, good. So thank you very much to Pavel and Weyven for inviting us. To present you basically the discovery of the Odderon, and thank you very much to Yuri also to introduce all the theory about the Odderon. So I will focus now on the experimental results. So what I will compare is basically proton-proton and proton-antiproton differential elastic cross-section, and see how it led basically to the possible observation of the exchange of this colorless C-odd gluonic compound, basically the Odderon. So first of all, I will do a very quick introduction to the Odderon, because you heard from the talk of Yuri, so you know everything about the Odderon now. Then I will discuss the data that we are using, experimental data from D0 and TOTEM. Then we will discuss how to extrapolate TOTEM data to tevatron energy, I will mention why we need to do that. And finally, compare between the two data sets, so D0 data and the TOTEM extrapolated data. So let me move, first of all, so what do we want to study? So as Yuri told you, we want to study elastic scattering. So this is basically proton-proton is going to proton-proton, or proton-antiproton at the tevatron is going to proton-antiproton. So what is the kind of signature for this kind of events? So you have a large rapidity gap inside where you don't see anything in the main detector, and we have intact protons or antiprotons in the final state. So if we want to measure this kind of events, the best way is to measure the intact protons and antiprotons after interactions. And as we saw in the previous talk, so the interactions are explained by the exchange of a colorless object, so either a pomeron or an Odderon, between the two protons. So how to explain the fact, I mean, in just a few words, that the proton can be intact? So what is going on at the LHC, the tevatron? I mean, I just put the example of the LHC. For many events, it's what is on the right diagram. Where you have proton-proton interaction, there is a gluon. I mean, it could be also quarks that are exchanged, but most of cases when they're at low X, gluons are exchanged. These gluons have a tendency to radiate a lot. So they emit plenty of gluons, so there is a lot of energy that is emitted between the two protons. And in this case, when there are lots of gluon, lots of energy that are produced, basically the protons are destroyed in the final state. So contrary to what you see in this diagram, the protons are destroyed in the final state. So what we are more interested in the left diagram, which is here, where we have this colorless exchange that happened. I mean, it was mentioned, it's Odderon or it is pomeron. So we'll have to distinguish between the two. If you want to put some evidence for the Odderon, clearly we need to understand what is the importance of the pomeron and Odderon exchange. And basically, so the signature will be two protons, for instance, in the case of the LHC, and nothing else. So this would be a very clean signature because we have a colorless object that is exchanged between the two. So basically now, let me say just a few words, I mean, to summarize what Yuri said. So what is the Odderon? So as Yuri mentioned, so there is some theory that have been expressed by Bartel, Fishinsky, and Prasalovich, which is a kind of a QCD vision for the Odderon, where there are multiple gluon exchange in hadron-hadron scattering. So you see these multiple gluon exchange, which are here shown in red. Originally, the Odderon was coming, I mean, from Nicolescu, as you know, and collaborators. And Basarab Nicolescu defined the Odderon as a singularity in the complex plane located at j = 1 when t = 0, and which contributes to the hot crossing amplitude. So this definition is a bit complicated. I mean, it was coming from Regis theory. So the way we see it in the Odderon in terms of QCD is the right diagram that I took from Yuri. Basically, where you have this pomeron that correspond to a two gluon exchange, and this Odderon that correspond to 3, 5, 7, and so on gluon exchange. So basically, that's why we call it odd for the odd number, whereas for the even number of gluon exchange, we talk about the pomeron. So as it was mentioned by Yuri, so basically this kind of QCD-inspired model or also Ringe-inspired model predict some differences in elastic d-sigma-dt between proton-proton and proton-antiproton collision. So what we want to study, do we see some difference between proton-proton interactions and proton-antiproton interactions? So this was the main question that we wanted to answer. So let me first describe, I mean, in this small schematic, what is the elastic cross-section d-sigma-dt as it could be seen at the tevatron in proton-antiproton interaction or at the LHC, which is, as you know, proton-proton interaction. So as we said, we want to study the elastic reaction. So there is an exchange of momentum between the two protons that remain intact in the final state. The idea is to measure the intact protons. I will discuss in a minute how it can be done technically. We use detectors that are called Raman pots. So what we do, we can count the number of events as a function of t, where t is the quadri momentum transferred squared at the proton or the antiproton vertex. And we measure this variable by tracking the protons through the magnets of the machine, so either the tevatron or the LHC machine. So what you can get is basically d sigma dt as a function of t. And what is expected is to have some kind of different parts on this d sigma dt elastic cross-section. We have, first of all, the Coulomb part, which is at very low t, which is proportional to t minus 2. Then you have the nuclear part, where you get an exponential decrease of the cross-section. And there is the region between the two, where you have some interference between the Coulomb and the nuclear region. We will mention in the later that it will be quite relevant for the measurement that we'll discuss. Then there may be some structures, as it was observed at lower energy than the LHC of the tevatron, where there were some resonances. And finally, when we reach higher value of T, you get the perturbative QCD regime. Okay, so that's good. So now let's see what tools do we have at our disposal to compare between proton-proton and proton-antiproton interaction. So the first thing they know that basically the tevatron was a proton-antiproton accelerator. And in fact, D0 installed some Raman pod detectors. What are Raman pod detectors? Basically, we call them Raman pod because the first one were developed by the Rome group. I think it was at the ISR, and pot simply because they look like a pot. So the idea is to have some detector that can move very close to the beam so that you are able to detect the protons that are scattered at small angles. So you measure proton-proton going to proton-proton, you have elastic interaction, and you measure that protons, or in the case of tevatrons, proton-antiprotons, that are scattered at very small angles. So the D0 Raman pod detector were installed about 20 to 30 meters, from the interaction point, and they were on both sides of the interaction point where D0 was located. So this is the measurement which is shown here on the left plot, where you have d sigma dt as a function of t, and you see that the D0 data are shown here as a function of black triangles. They correspond to about 30 inverse nanobarn of data, and they were measured in the domain of t between about 0.26 up to 1.2 GeV squared. So now let's go back to the LHC. So at the LHC, you know that it's proton-proton collider. So it was the same. Basically, both the two main experiments at Atlas and the CMS, there were some Raman pod detectors installed close to the main experiment. So for Atlas, it's called Alpha. And for CMS, there was an independent collaboration called the TOTEM that allowed to measure intact protons after the interaction inside the CMS area. So this is a view, for instance, of the Raman pod detectors that were used inside the TOTEM experiments. And again, we measured proton-proton going to proton-proton elastic events. So I must mention that these Raman pod detectors were located at about 220 meters from the interaction point. So let me just show you what is the forward coverage in CMS TOTEM, because we have elastic collisions. So what we want to measure is the two protons, and request a veto of what is going on, for instance, in CMS, which is around TOTEM. Or also, there were some special detectors and special telescopes that are called inelastic telescopes that were installed by the TOTEM collaboration. They were called T1 and T2. So they cover the domain in rapidity between about 3 to 4.7 and 5.3 to 6.5. And they were used as a veto to veto the inelastic interaction. Because again, we want to measure elastic events, which means the two protons are intact and there is nothing else. So now let me discuss also the fact that this measurement benefited a lot from the good data at the LHC. In fact, if we want to have a plot which shows the sigma dt as a function of t, what is shown on this plot, there is just a sketch of the cross-section at different square root of s. So first of all, I want to mention that there were plenty of different center of mass energy that were used at the LHC. As we will see in the following, the TOTEM collaboration took data at 13, 7, 8, and 2.76 TeV, and this will be crucial for what we are going to do. And also, there are different ways of introducing the beams inside the LHC. What we call, in fact, is the beta star, is how the beams are basically colliding, between the two. So if you are at very high beta star, it means that the beams are extremely clean and are almost parallel between themselves, which means that we can go very close to the beam and measure data or measured scattered proton at very, very small angles. So by having these different values of beta star, I don't enter in the detail of the definition, but going down, for instance, to 2.5 kilometers for beta star up to something like 90 meters, we are able to cover a very large domain in T. So you see between these very low values of T, like it's going down to 10 to minus 3 up to a few GeV squared in T. And this is also crucial if we want to measure precisely the elastic cross-section. So now let me describe, just to mention that the measurement that we are going to use to do this comparison between the D0 and TOTEM data. As I said, so the TOTEM collaboration to data 2.76, 7, 8, and 13 TeV, so they're illustrated on the bottom plot for 3 center of mass energy. The right one shows the data at the center of mass energy at 13 TeV, and you don't even see the error bars on the points. They show that the kind of precisions of the elastic cross-section, since basically the elastic cross-section is so high, if you have a few days of data, you get a very precise prediction on the measurements. And just as a reference, I show in the middle the 2.76 data and the 8 TeV data on the left. Okay, so now let's discuss a bit the strategy. And if we want to discuss the strategy, it's good to put all these data sets, again, 13, 8, 7, 2.76, on the same kind of plot. So you see basically the characteristic of this data. So I will mention later the open points, which is 2 TeV. That's not a measurement, it's an extrapolation. I will discuss this later. But for these 4 center of mass energy, you see that these data, they all have the same structure. They all show a decrease of the elastic cross-section as a function of T. They reach a kind of minimum that we call a dip. Then they increase, reaching a maximum, basically, and then decrease again. So we see always the same kind of structure. Whereas if we go back a few slides going to the D0 results, this kind of structure was not visible in PP bar interaction. So this was the starting point of this idea, is to characterize basically the shape of this kind of cross-section and try to compare the PP and PP bar data set. So it's illustrated on this plot. Again, it's purely a sketch until now. So this is the elastic, the sigma dt cross-section. I identified some kind of key parameters for this cross-section. So the obvious one, as we just discussed, is the dip and the bump, which are here. So there are the 2 points that are characteristic of this elastic cross-section for PP interactions. We add additional points. For instance, the same value of the sigma dt as the dip, but higher T value that we call dip 2. There is mid1 and mid2 that correspond to half of the cross-section between the dip and the bump. So we call them mid1 and mid2. There is also bump 2. Bump 2 is the same values of d sigma dt as the bump, but at low values of T, basically this decrease of d sigma dt. And in addition, we introduce 2 other points that we call bump plus 5 and bump plus 10 that correspond to the position in T and d sigma dt when we have 5 times the difference between the bump and the dip in the cross-section and 10 times the difference. So this is the kind of characteristic point, the list of characteristic points that we choose. This is, of course, somewhat arbitrary. We choose 8 points to describe basically the shape of this cross-section, and we could have chosen 10 or 6, but it's kind of arbitrary. And in addition, I would like to mention already that our approach wanted to be as model independent as possible. For this, we use the data points that are closest to those characteristic points. So we don't do model-dependent fits, for instance, to determine exactly where is the bump and using a fit. We just choose directly the data point that is closest to the real bump. So if it's just close to there, we choose that data point without touching that data point. In the case that there are 2 adjacent dip or bump points, for instance, about equal value, we just merge the data bits. Okay, so what is the first thing? Before going to any detailed analysis, the first simple idea that we considered, and which is natural, what is the ratio between the bump and the dip in proton-proton and proton-antiproton interaction. So this is illustrated on this plot where you show this ratio R, which is basically for the bump over dip ratio. This is, first of all, for PP interactions. You have the ISR results, which are at lower energy, which is this part of the curve, and they are compared to the TOTEM data, which are here in black, and also the extrapolated of TOTEM data at the same square root of S as the tevatron, which is 1.96 TeV. And this is compared to the PP bar measurement, which are here the open points. And we see clearly already from this point of view that we have a difference indeed between proton-proton and proton-antiproton interaction. So D0 data, which is the black point here, the empty point, shows a ratio of about 1.0, since there is no visible bump or dip for the D0 data. So we see already about a 3 sigma difference between proton-proton and proton-antiproton elastic data. But what we wanted to do is something a bit more quantitative. I mean, going back one slide, I mean, we don't want to use only this dip and the bump, but we want to use the full shape and basically all these characteristic points that we defined before. So now you will ask me, okay, but I mean, it would be much easier to compare if we had the, let's say, proton-proton measurement at the same energy as the tevatron, 1.96 TeV. Unfortunately, it's not possible because, I mean, there is no acceptance at this square root of S to measure elastic proton-proton data for the Raman pot detector. So there is no possibility, even if we were running the LHC at such low energy, which is difficult, we will not have acceptance to do the measurement in the dip and bump region. That's why we need to extrapolate the LHC measurements at 2.76, 7, 8, and 13 TeV down to the tevatron energy, which is 1.96 TeV. Or in other words, we have to see how this point, both the T value of this point and the D sigma dt value vary as a function of square root of S. And this is exactly what we did. So let me show you the plot. Basically, what we show here is the T value as a function of square root of S of all these characteristic points. So you remember for this, for instance, the bump and the dip that we discussed many times. And there are all these 6 characteristic points, dip 2, mid 1, and so on and so forth. And we show the T value of this point at the same time as the cross-section, elastic cross-section d sigma dt as a function of square root of S. So the basic idea is to use the measurements. So we have these 4 data points that are measured at this 4 square root of S and extrapolate them to the tevatron energy at 1.96 TeV. So how do we do this? We used, in fact, very simple fit. I mean, this is the value that we obtain T, which is linear in log square root of S, and d sigma dt linear in square root of S, in order to predict what is the value of this characteristic point at the tevatron center of mass energy. And we do it for these 8 reference points. I should mention that we also tried alternate parametrization, and it gives basically to a compatible result within uncertainties, and also it leads to very good chi-squared per degree of freedom, which is better than 1. So this is what we obtain, I mean, concerning the fit, and the stars are the values which are predicted now at 1.96 TeV from proton-proton interaction. So what is the next step? The next step, I mean, we have now, if we go back a few slides, basically the value of this characteristic point at 1.96 TeV, and we would like to compare to the D0 measurement. So the last point is definitely to predict what would have been the TOTEM measurement at 1.96 TeV if we were able to run at this energy at the same values of T as the D0 measurement. So in order to do this, we fit this reference point extrapolated to 1.96 TeV that I just presented from the TOTEM measurement using this double exponential fit, which is here, which is basically as a function of T at 1.96 TeV. So this gives a chi-square, which is really good, about 0.6 per degrees of freedom. And in fact, there are a sum of 2 functions. The first one is basically is rapidly falling as a function of T, and the second one is increasing at higher T, and they cross basically around the dip. So of course we use the full correlation matrix, I mean, between the data points to consider the uncertainties. And I should mention that this formula is also leading to a good description of the TOTEM data at all square root of S. So Now, I mean, there is also one step that I put a bit under the carpet until now. So what about a difference of normalization between the de Giraud measurement and the extrapolated totem data? For instance, I mean, there is a luminosity uncertainty, so there can be also this global difference in normalization. So we take the difference in normalization into account by adjusting the totem and the zero data set to have the same cross-section at the optical point, as also Yuri mentioned, so d sigma dt at t equal to 0. So how do we do this? The first step, as usual, we need to predict the total cross-section from proton-proton interaction originating from totem data. So the totem measurement, so we have here the total cross-section as a function of square root of s. So the totem measurement are the black points. And again, we fit this black point as usual to extrapolate the value of sigma tot at 1.96 TeV. So this gives you this value of about 83 plus or minus 3 millibar. So from this value of the total cross-section, using the optical theorem, we can extract the value of d sigma dt at t equal to 0, using this, again, this formula which is here. And in fact, so this leads to a totem d sigma dt at t equals 0 at the optical point of the order of 357.1 millibarn per GeV squared. D0 measured the optical point at d sigma dt at small t, so for pp bar interaction to be of 341. So that's why we rescale the totem data to the D0 value by this factor, which is about 0.954. There is just a small warning. Of course, we do not claim that we perform the measurement of d sigma dt at the optical point at t equals 0, because this would require much more data at low t, which we don't have. But we normalize both data sets to a somewhat arbitrary value, basically, which is the value published by D0, 341. Okay, so now let's move on, and we get basically the key plot, which is the money plot, which compares directly the data from the D0 measurement to the extrapolation made by TOTEM. So the value of the pp bar measurement by D0 are the blue points, which are here, and the value that we obtain from the pp extrapolation, by TOTEM, are the red triangles, which are shown here. So you already see on this plot, only by height, before doing anything quantitative, that indeed we see some differences between the two measurements. So now the question is, how are we going to quantify this difference? So this was basically the next step. So as usual, we need to do a chi-squared test to examine the probability for the D0 and TOTEM differential elastic cross-section to agree. So the important point is that we want to do the test using the difference of the integrated cross-section in the same T range that we have the D0 and the TOTEM measurement. We cannot do this comparison in a domain where there is no data set. That's why we restrict this comparison in the common data domain between TOTEM and the D0. So given the constraints on the optical point that I just mentioned, normalization, and also logarithmic slope of the elastic cross-section, we obtain the chi-square test, with 6 degrees of freedom, gives a p-value of about 6.1 10 to minus 4. And this corresponds to a 3.4 sigma significance. So basically, by comparing the data of D0 and TOTEM, we get already the significance. So now the idea is to combine it with a previous measurement that was performed by TOTEM and published already. So where there was a measurement of the rho parameter and the total cross-section, and this is also an independent indication of the Odderon. So why is it an independent one? In fact, so this is illustrated, for instance, these two plots, at 13 TeV. And in order to measure rho, we need to go to very small t, which is further away from the value that D0 measured. So TOTEM did this measurement, for instance, at 13 TeV again. So, and we are using this very, very low t measurement in order to measure the parameter rho and also the total cross-section. This is illustrated on these two plots where you have the total cross-section as a function of square root of s, and there are difference fit, which is a log s and log square s in blue, which is a pure log s in green, as an example. You see the total cross-section as a function of difference square root of s, they favor this kind of blue fit, which is here. And when you go to the rho measurement, you see that, in fact, the data at 13 TeV, which are the red points, they favor this log S dependence, which is green. So this is coming, what is called, from this complete parametrization of the total cross-section and row parameter without any Odderon, I should mention. And you see that basically, if you don't have any Odderon, you have difficulties to describe the data set of the total cross-section and the row parameter. So it was an independent evidence from the TOTEM collaboration to see that indeed we need the Odderon. Again, we can combine both of them because they are coming from completely independent data set. So we combine now these two results, the previous one from TOTEM and this new result that I detailed at the comparison between PP and PP bar interaction. So for this rho and sigma tot measurement, this was a 4.6 sigma significance. And if we combine it with a new measurement, so with all these models that I introduced you by Compete, we get a significance of about 5.7 sigma for the T-channel exchange of a colorless C-hot gluonic compound or the Odderon when we combine both results. There are other models, like for instance, the one made by the Durham people. And so depending on different models, we obtain a combined significance between 5.3 to 5.7 sigma, again, depending on the model. So it brings me basically to the conclusion. So what I showed you, first of all, is a detailed comparison between proton, antiproton, and proton-proton data that were done. Already, if we have the R ratio of the bump over dip, it shows a difference of more than 3 sigma between PP and PP bar interactions. Then we did a more detailed analysis, more complete analysis, which is characteristic of the shape of the elastic cross-section for PP or PP bar. And we fitted 8 characteristic points. So this led to a cross-section difference with a significance of 3.4 sigma. And we combine it with the row and total cross-section result. We obtain basically 5 sigma when we combine the two results. And this constitutes the first experimental observation of the Odderon. So basically, there were already some signs at the ISR, something like 3 sigma, that between observing PP, the difference between PP and PP bar interactions. But at the combining the data across the Atlantic, we were able to have some observation of the Odderon. So thank you very much.
Thank you. We already have a few questions lined up. Let me see. Okay. Wojtek?
All right. Hello, Christophe. Can you hear me?
Hello, Wojtek. Yes, thank you.
So I just, for everybody else's information, I've had this discussion with Christophe more than once. The problem is that it's never enough time to really have a discussion. So I still need to raise my points again. I don't know where to start really, because I always question this issue of a model-independent result. It's true that Christophe or this analysis does not have a dynamic model dependence, but it has its parametrization, which makes it a model also. Hence, it is not in my opinion, a real model-independent measurement is comparing data to data. So it is so I want to make that statement again, that this is not totally model independent. It has a parametrization.
Yeah, as you know, Wojtek, basically, we did the best that we could, because we don't have the same PP measurement as the same square root of S. So what we tried, there are not that many functions that we can use. As you know, we have basically 4 points to fit, so we cannot have more than 2 parameters. That's why we choose very simple functions. So these are 2 of them. And as I said, we use basically other parameterization. They are leading to basically similar results. But what I would like to stress, and this is something maybe also deep from the theoretical point of view, I don't know, that the fact that we can use the same parameterization for all these is not obvious. I'm getting some echo, but it's not obvious, and it's mainly some theoretical results, because the fact that all these characteristic points at the same square root of S dependence it's not obvious to me that it was kind of surprised that even the same function is working for all these points.
Correct. Except that you're looking around the corner a little bit. And I just want to make that point that it's not exactly model independent. You have your parameterization, and history of elastic scattering is actually looking around the corner. It doesn't always work. We know the famous story of the rise of the total cross sections and so on.
Yeah.
Can you, I'm sorry to apologize to the organizers who want to have, but I really think it's important discussion. Regarding to your latest comment, did you investigate how some systematic uncertainty due to your choice of points, if you move them maybe to the right or to the left, do you get a different result? Because that could affect your extrapolation, right?
Yeah, so basically the way it's done is that we are using the full uncertainty matrix for all these points. I mean, for the Earth treatment, that's why both in T and the sigma dt. So this is basically this illustrated maybe on, again, the same kind of plot, because we have the values, the T values that we have, and they have their uncertainties. I mean, like for instance, we see all their uncertainties, and also the d sigma dt uncertainties. So that's why we use basically these full uncertainties into account. So both of them in the analysis. Yeah.
Okay, so okay, but it would be nice to see a number how things change if you change within 1 sigma or so. And then I have two more shorter comments. I also want to, as I mentioned before, this combining of result experiment minus theory and the difference between two experiments sounds an odd, to use the word, not pun intended, way to get the final result, because typically you would combine two theoretical uncertainties based to the experiment minus theory, or like particle data group does, you would combine two experiments to get a better estimate of whatever significance you want. So this is to me a little bit odd way of doing things. And if you can you find a reference and you can send it to me, whether of other places where it was done.
Yes. So in fact, I mean, it's a kind of combining two experiments. I mean, as I said, I mean, there are different measurements, in fact, even different detectors, different way of going close to the beam. So as if we were combining two experiments. But I can send you offline, I mean, some papers that were published also doing this kind of combination, and this happened already in the past, that were published, for instance, in PRL. But I can send it to you offline.
I mean, I tried to find them myself. The last thing is your normalization. I don't quite understand, because you are extrapolating with some method to t equals 0, right? And then pp and pp bar. And then you say that they should have the same value or something. And I also, from the region where you are, as optical theorem doesn't work. So I don't know what gives you this, the reason to state that these two extrapolations to t equals 0 should be the same. And this is my last question in case the organizers are concerned. Yes.
Yeah. So basically, that we know that the cross-section at the optical points are expected to be equal if there are only C even exchanges. So there is no Odderon. So that's why we choose to normalize, I mean, to the cell, this first point, to normalize at the sigma dt at t equal to 0. And again, as I said, we normalize it to an somewhat arbitrary value, because we don't claim that we measure this value. But we use the d0 measurement, so we don't touch it. I mean, that's it. And then we extrapolate the values of TOTEM using this formula. So we predicted, as I said, sigma tot. So we obtained from there the sigma dt at t equals 0. And we adjusted the TOTEM extrapolation to the value of d0. So what we tried, of course, is what would be the effect, because, I mean, if there is an Odderon, and we find indeed that there is an Odderon, and in fact, the change on the sigma dt at t equals 0 is much smaller than the uncertainties that we have here, that I quote also on the next slide. The uncertainties that we have is basically a bit more than 10%. You see for this value of D0, and this was the prediction from TOTEM. So the difference that would be observed on d sigma dt at t equals 0 because of the existence of the Odderon is much smaller than this by far. So that's why we could adjust them. I mean, even if there would be a small difference due to the Odderon.
But in order to make this comparison, you have to extrapolate from smaller t's. You cannot extrapolate from your depth region. So
yeah, but again, that's why I'm telling that we use the data that we have and we normalize it to an arbitrary value. We don't claim, where did I put this? Where did I put this? Probably later.
I think you have it, that you don't. You're not claiming that you do it, but you're using that extrapolation anyway.
No, but I mean, let's say that I wanted to normalize not to D0 340, but to 1,000 millibar per GeV squared. It would be fine. The only thing that I want to do is to put a common normalization between the both data sets. And this, we choose to use the value of D0 since D0 measured it, but we could have done it in the same way, normalized to any arbitrary value, 1, 1,000, 1 million, if you prefer. It doesn't matter. That's why we don't say that d sigma dt at t equals 0 is this value. We want just to normalize both data sets between each other. So it's not a measurement of this value at t equals 0. I completely agree with you that if we wanted to claim a measurement, then we would need much more data set. I mean, towards t equals 0, this is for sure.
Yeah, may I suggest the discussion gets a little technical, and we have a cutoff as well as 2 more questions in the pipeline. And so maybe Jamal can ask the second question.
Okay, thank you. Thanks, Christophe. Very nice talk, both Yuri and you. I'm a bit confused about what is exactly the claim. So always people thought, well, total cross-sections are dominated by non-perturbative physics, and pretty much all the models of the Odderon, at least the ones Yuri mentioned, these are very perturbative objects. What is the logic behind that, using perturbation theory to do total cross-sections? And the related point is, even if you try that, the T is so low, wouldn't you expect to have what Yuri mentioned as saturation and nonlinear QCD effects dominating there?
So I don't know if Yuri wants to say something.
Yeah, can I jump
say
in?
What we,
So Jamal, thanks for the question. If you noticed, you're right. I was talking mainly about perturbative calculations, though I did mention a CFT calculation by Chungi, Tan, and collaborators. The point is that nobody, I did not show you a single prediction for PP or PP bar, right? So indeed, what I'm discussing is was largely perturbative, and it is hard to directly apply it to PP and PP bar collisions. So as far as quantitative comparison of theory with the data, that is a tough question, and you're right, we have to think of non-perturbative effects, we have to think of saturation effects if we're at low T. I know in my talk I do mention some works by Zhenya Levin and his group, and by Misha Brown, and using small x nonlinear evolution for the Odderon. I don't know how close they come to even try to describe the data. But I think you have to disentangle 2 things, right? One is Christophe's money plot, that d sigma dt in PP and d sigma dt and PP bar at high energies are different. And modulo all the questions, all the maybe very good questions Vlodek was asking, this is the main claim, that the 2 cross sections, on slide 18, the two dots, the blue dots and the red triangles are different. The blue dots are PP bar measurement by D0. PP is the totem measurement extrapolated to D0 energies. So that's the essential qualitative statement. From the theory standpoint, we can say that perturbation theory expects an Odderon. CFT, non-perturbative physics, expects the Odderon. But you're right, we're not there yet to give Christophe a curve to compare. with. So that's a very good point. But qualitatively, I think there is a statement here. Agreed?
Yeah. And experimentally, so this is basically what we say. We see this kind of difference, and the natural explanation is basically via the Odderon. This would be to explain this difference. But I agree that also measurement maybe at higher T with more data and so on would be also something interesting. Maybe then perturbative calculation would be valid and something like that. This would be interesting to study.
Maybe I can just a very short comment or question. So if I were to push my luck and take the extreme opposite view, are there models of what you refer to as compound gluonic state? What if I change the game and say, are there models of compound hadronic state exchanges, which will be colorless by default and maybe C odd? Can one make one?
I think you're talking about region exchanges.
Exactly. So that's the point, that the good old Reggie theory, as you know better than me, is not clear what it has to do with quarks and gluons or perturbation theory.
No, so regions, when you have T-channel quark exchanges, they fall off with energy as roughly 1 over square root of energy. And my expectation is by Tevatron energies that are being considered here, they will all die off. And Christophe can also comment, he had the slide in the beginning that that regions would also have resonances in d sigma dt, some structure in that cross section, and they don't see it. So they're confident that they don't see any regions. Yeah, please, Christophe.
Yeah, sorry that this plot is a bit small, so I should have taken maybe a better plot. But we see that basically this is a certain TV, for instance, for this right plot. And you see that there is no structure at all. I mean, it's very smooth dependence, at least to a T, which is 4 or something like that. Whereas when we were at the ISR, you had all these resonances because you had the different exchange, meson exchange, and so on. You had the region exchange. And it doesn't seem to be the case at very high energy for PP interaction. It's really a smooth distribution as a function of d sigma dt.
I see. Okay, thanks.
Can I ask now?
I'm sorry. We have several questions in Vlodek. I think.
No, it's not Vlodek. It was Zhenya, and I think it's his turn. Sorry, Pavel.
Oh, sorry.
Yeah, it was Zhenya, yes.
That's right. Christophe, I have some doubt. What is strange to me is the following: from TOTEM data at 13 TV, you need to contribution to real part of the amplitude, which is negative, right? Which is negative. It's smaller than compete whatever did, right? So you have some negative contribution at T equals 0, which you assign to Odderon. In the deep, contribution of Pomeron in the real part is negative. So to have deep in proton-proton, you have to add a positive contribution from Odderon. In this case, you have deep in proton-proton and shallow deep in proton-antiproton. So to me, I see some contradiction between data at 13 TV at T equals 0 for real part and what you're showing now in this slide 18. Do you understand what I'm saying?
Not really. I mean, I don't fully understand what you mean. The only thing that we saw, I mean, what we...
how you get different deep in proton and proton-antiproton. You need to have
what is clear is that
interference between real part of Pomeron exchange.
Yes.
Not one Pomeron center. And
yeah. What we measured again is the dip and the bump, or this characteristic point at this different square root of S, and we saw how they evolve.
How you feel the dip. So in the dip, imaginary part of contribution of Pomeron is equal to 0. That's why you have a dip. So you feel the dip adding real part of your amplitude. Your real part consists of, as Yuri said, consists of Pomeron contribution plus or minus Odderon contribution. So Pomeroy contribution in the point of dip is always negative. If I'll have more time, I'll explain why it's very easy. So if Pomeroy contribution, and I have not seen any model where it was different.
Zhenya, may I just jump in and say that it's a good question. I don't think we can resolve it on the spot. I am not 100% sure your statement is model independent, so one has to discuss that further.
No, the fact that real part is negative is model independent. I'm sorry. I know. Okay, if you show me the model where you have positive real part of Pomeroy, I will agree with you.
For
But
the totem
I
data,
never saw.
for the raw,
For
the raw
Pomeroy,
parameter.
for no, not raw parameter. I'm sorry. I'm talking the real part in the point of dip. No. At t equals 0, a different story. Real part in the point of dip for distribution is always negative. In the point of dip, not at t equals 0.
I thought it's positive.
No.
Oh, you mean the real part of
Pomeroy
is negative? Yeah.
No.
Okay, but well,
of Odderon, sign should be such that have real part smaller for proton.
Well, Zhenya, alternative way of thinking about the deep, totally maybe different from what you're saying, is to think of it as a Fourier transform as it is from the B space, from the impact parameter space, and that's just a zero of the Bessel function. I don't know, is it really the same? Would it have exactly the same features? I don't know. Is it?
It's the same. It's the same.
Okay, well, like I said, I don't have a quick answer to your question, but you know, the data is data.
Yes, what I was telling you. Basically, what we claim is what we observe directly from the.
First of all, they have some confirmation that in some point I'm right, because they fit the dependence of the point of dip the function of energy. And you have their log behavior. What in slide 13, he has two formulas. What this I expected from that model which I told you, and they have experimentally. And this is really crazy. I mean, the sigma t proportional to square root of s. I agree with Vlodek. I don't know how to explain this. It's something. But what this thing is really just support my simple idea how the origin of the dip.
Yeah. And this is again some experimental observable that we see from the data. Again, with these 4 points,
Yeah,
this
I know that you can say it's not a large range of energy, whatever. But theoretically, Yuri told you everything you have or constant piece energy or falling down.
And from this point of view,
how you
get
the square root of s, it is crazy.
Yeah,
okay,
what was really crucial from So it was really crucial to have the measurement at 2.76 TeV, because I mean the range of extrapolation to 1.96 is not that large from these points, basically. So it was really crucial to have the data at 13, 8, and 7, and especially the 2.76 TeV data. Because without the data at 2.76, I mean, it would have been probably a too large extrapolation from 7 down to 2 TeV. So these data were really crucial. So it was thanks to the LHC that could run at this lower energy at 2.76 TeV.
All right. Sorry, it's 11, and I think Christophe have a class to teach.
Yeah, I have to give my lecture now.
Now, thanks
I need
everyone
to
for
disconnect.
coming.
I need to disconnect.
Recording. If some of you want to continue discuss a little bit more, I will leave the Zoom open. But we also have a nice comment from you two on the nice talk and updates from both of you. And
okay.
Right. So I think Yuri can stay.
Thank you. Yeah.
But Christophe.
I need to leave to give my lecture, so thank you everybody, and talk to you soon, and send emails. I mean, by anyway, if you have questions, comments, so thank you again.
Thank you very much, Christophe, for the excellent talk.
Okay, thank you, Christophe. I will get to you on offline, but I just wanted to mention some points, because actually one crucial point is that this common normalization that was discussed. So as you know, we have studied this question. We have published a paper actually about the Odderon evidence, which is a few author paper. It's not using model dependent formulas or S or T dependent extrapolations. We see even bigger evidence for the Odderon than quoted by TOTEM D0, but using different, slightly different data